Hey guys, in this video I'm going to go over cafe performance standards and the rebound effect. In the course we've considered three different regulations for environmental policy. One is the corrective tax, another is tradable permits or cap and trade, and the third are performance standards. CAFE references the corporate average fuel efficiency standard. The rebound effect references an unintended consequence of this type of regulation. It's one of the reasons that many economists have a preference for either the corrective tax or tradable permits as a market mechanism to arrive at the socially optimum or the socially optimal outcome. All right, so what's the deal? Let's start with the key insight based on our driving example. People care about driving, not really gasoline. What does this mean? If the price of driving goes down, there's going to be more driving. That's exactly what happens when we increase our fuel efficiency. If our fuel efficiency goes from 20 miles per gallon to 40 miles per gallon, then the cost to drive 1 mile has gone down substantially. What do we know from our basic microeconomics? That if price goes down, then quantity demanded is going to go up. So if the price for driving 1 mile goes down, then the quantity of miles people are going to want to drive is going to go up. As a consequence, that's going to affect the demand for gasoline. So a change in demand for driving affects gasoline demand. In particular, it's a change in quantity demanded. Let me address that for driving. So gasoline demand is going to depend on demand for driving. There's a relationship between these two equations. In class I've talked about derived demand. What do I mean by that? All it's saying is that the demand for gasoline is derived from the driving demand equation. So let's take a look at some equations. Right here I have an example of a demand equation for driving miles. PM is the price per mile, QM are the number of miles driven. And as we see, there's a negative side, so we have a downward demand curve for driving miles. We're going to take advantage of two identities. The first one relates the price per mile driven to the price of gasoline via fuel efficiency, miles per gallon. This should make sense. Price per gallon divided by miles per gallon. The gallons cancel out and we're left with price per mile. That's why this identity holds. The second identity relates the quantity of miles driven to the quantity of gasoline consumed. It's also going to be related via the fuel efficiency or the miles per gallon. This should also make sense. The units on QG is gallons. The units on miles per gallon is, well, miles per gallon. And so the gallons cancel out and we're left with miles, which is exactly the units on QM. So these two identities hold. They relate the price for driving a mile to the price of gasoline, and the quantity of miles driven to the quantity of gasoline consumed. So, looking at our original demand equation for driving miles, we can just substitute in these identities into this demand expression, and we'll get the equation in terms of PG, the price of gasoline, and QG, the quantity demanded for gasoline. When we do that, substituting this guy into here, we're just left with this on the left-hand side, and then substituting this into QM in this equation, we arrive at this on the right-hand side. If we multiply both sides of our equation by miles per gallon, we're going to be left with price per gallon on the left-hand side. Multiplying the miles per gallon on the 100, we get this for the first term. And then notice miles per gallon is already in the second term, so when we multiply both sides by the miles per gallon, we're left with miles per gallon squared. Once we have this, then we can figure out the demand for gasoline given any fuel efficiency. So for example, under an initial technology with a fuel efficiency of 20 miles per gallon, then our demand for gasoline is going to be PG equals, put the 20 in, we get 2,000, and then put the 20 in here, we square it, we get 400 divided by 10, and we're going to get 40 QG. This is our demand for gasoline under the initial technology. Let's graph this. $2,000 was our y-intercept. We can solve for our x-intercept by setting our equation equal to 0 because this represents 0 price. So we have 2,000 minus 40 QG. So solving for QG is going to give us 50 because 2,000 divided by 40 is 50. So our y-intercept, let's put our x-intercept, is going to be there. So our demand for gasoline under the initial technology looks something like this. Let's look up at this box. What do we want to find? Well, we want to find the quantity of gasoline that's going to be used, the miles driven, the price per mile, and the consumer surplus. We might have other quantities of interest, but these are the ones I've talked about in class. To figure out the quantity demanded, we need to assume some price. So let's say the price of gasoline is 200 cents per gallon. Well, on the y-axis, let's say this is about 1,000, we're going to get 200 cents per gallon, right about there. Remember, our line is really a function, and we can use it to define the relationship between price and quantity demanded. What we see, this is going to intersect our demand for gasoline right about here. If we plug that 200 in, we're going to get 45. How? Price of 200, this is 2,000, minus 40 QG, and then solving for QG, we're going to get QG is equal to 1,800 divided by 40, which is our 45. So the quantity demanded at a price of 200 cents per gallon is going to be 45 gallons. So we have our quantity of gasoline. Figuring out miles driven, it's pretty straightforward because of this identity. We can take the quantity of gasoline consumed, which is 45, and multiply that by the miles per gallon. This should make sense. If I'm consuming 45 gallons and my car gets 20 miles per gallon, well, I just multiply those two together and I get 900 miles. So I'm going to drive 900 miles. The price per mile, we can also take advantage of this other identity. So the price is 200 cents per gallon. The miles per gallon is 20 miles per gallon. So 200 divided by 20 is 10 cents per gallon. So I'm going to be paying 10 cents per mile. Excuse me. So I'm going to be paying 10 cents per mile driven. The last thing is consumer surplus. You guys are excellent at calculating consumer surplus at this point. Remember, the consumer surplus on the first unit consumed is the difference between the private marginal benefit curve, which is our demand curve, and the price paid, which is 200. The second unit of consumer surplus, the third, so on and so forth. This is our consumer surplus under the initial technology. Next, rather than consider a new technology that maybe increases the fuel efficiency, say, to 40 miles per gallon, let's consider what the government's objective might be. Let's suppose the government wants to reduce fuel consumption by 50%. So looking at our graphic here, the government may want to reduce fuel consumption from 45 to somewhere maybe about here, 22.5. That would reduce fuel consumption by 50%. We learned with the corrective tax that the tax can help us. It basically increases the price of consumption. And so we can use that here. If we want to reduce consumption to 22.5, we could set a price that's somewhere up here on the y-axis. If we set our price with the tax right here, so P plus tax, this is the price that the consumers pay at the pump. That is the pump price. They pay this price, they're only going to consume 22.5 gallons. Let's think about how this is going to affect some of the other measures of interest. If we're consuming only 22.5 gallons, then our miles driven is going to go down because we have the same fuel efficiency, but we're consuming less gasoline. So consumers don't like that. The price per mile, well, the price per mile is going to go up quite a bit because the price per unit of gasoline has gone up. Before, the price per mile was 200 cents divided by 20 miles per gallon, or 10 cents per mile driven. Now, we're essentially just increasing the price per gallon of gasoline without changing the fuel efficiency. So that means the price per mile driven under the tax is going to go up. Consumers don't like that. The clearest way to see how consumers are affected, I would argue, is to look at the consumer surplus. Well, what happens with the consumer surplus under the tax. Now consumers are only consuming 22.5 gallons and they're paying a higher price. So the consumer surplus is considerably less under the corrective tax. Consumers do not really care for the tax. In fact, producers don't really care for the tax because now they're selling a lot less gasoline. This is part of the reason energy efficiency policies or performance standards are so attractive, because they are going to turn out to be really advantageous for consumers. Let's take a look now to see why. Let's go back to our derived demand equation, or our demand equation for gasoline. We solved for it in terms of miles per gallon. Let's suppose with a new fuel efficiency standard, we've increased it to 40 miles per gallon. Why is that? Well, we might choose that because the objective is to reduce fuel consumption by 50%. So if we double the fuel efficiency, if we hold all else equal, we should arrive at our 50% reduction in gallons of gasoline. So in theory, we want to still arrive at 22.5 gallons of gasoline consumed by increasing the fuel efficiency to 40 miles per gallon. That is doubling the fuel efficiency. Let's see what happens when we do that. Well, our demand equation under the new technology is going to be PG 100 times 40, so that's 4,000, minus 40 squared divided by 10, that's going to be 160 times QG. So let's depict this demand curve. So now the y-intercept is going to be up here. And the x-intercept, well, we can solve for that by setting this equal to 0. So the x-intercept will be 4,000 divided by 160, which equals 25. So that's right about here. So our demand curve, if I can get it, is right about there. Let's see what happens under this new demand curve. Well, we no longer have a tax. The price is back at 200 cents per gallon. Let's take this 200 cents per gallon and go over to where that intersects the new demand curve. And what we see is that it intersects the new demand curve to the right of 22.5. Consumers are actually going to consume more than 22.5. It will be 23.75 gallons. So consumers, that's the rebound effect. Consumers are not going to reduce their consumption to just 22.5 gallons. There's going to be a little bit of a rebound effect, or maybe a really big one. In this case, it's pretty small. Miles driven. Well, they're consuming 23.75 gallons, but the miles per gallon is 40. So 23.75 we're going to get 950 miles. So we're actually driving more miles under the new technology than the initial technology without the tax. Remember, that was just 900 miles. So consumers are going to be happy because they get to drive more miles. The price per driving mile has gone down substantially. Why? the price of gasoline's 200, the miles per gallon is 40 miles per gallon. 200 divided by 40, that's 5 cents per mile. Under the initial technology without the tax, they were paying 10 cents per mile. So this is quite the price reduction in terms of the price per mile driven. Finally, let's use this new demand curve to think about consumer surplus. Well, consumer surplus, the first unit of consumer surplus is all the way over here and goes down to 200. The second unit of consumer surplus, the third, so on and so forth. What you see is that consumers' surplus is much greater under the fuel efficient vehicle, so the 40 miles per gallon, much greater than the initial technology, consuming out to 45 gallons of gasoline, and much, much greater than the consumer surplus under the corrective tax. So consumers really win with the energy efficiency improvements. So it's part of the reason that these are really politically attractive regulations. Finally, let's look at this table to think about, let's put the math aside, let's see if the differences in gasoline used, miles driven, price per mile, consumer surplus, and externalities between the new technology with 40 miles per gallon versus what's delivered under a tax, if it accords with our intuition. Is there going to be more gasoline used under the new technology or the tax? We see right here that there's 23.75 gallons used under the new technology, whereas the tax actually delivers the full 50% reduction in fuel. So there's actually more gas used under the new technology. And this is exactly what the rebound effect is referencing. Are we going to drive more miles under the new technology or the tax? We see we're clearly going to drive a lot more miles under the fuel efficient technology. Why? Because looking at our identity, we're using more gasoline than under the tax, and our miles per gallon is greater. So if both of these are greater, then of course the miles driven is going to be greater. Which is going to be greater? The price per mile paid from the consumer perspective, that is the pump price, under the new technology or the tax? Well, the price per mile driven is going to be the price of gasoline divided by the miles per gallon. So under the new technology, there's no tax. We have 200 divided by 40, which is the miles per gallon under the new technology. So we have 5 cents per mile. Under the tax, our price paid by the consumer is much greater, much, much greater, and the miles per gallon is still 20. So if the numerator has increased, which is certainly the case, this is the price paid by consumers under the tax, that is the price plus the tax, and the miles per gallon, the denominator goes down, well, the price per mile is going to go up a lot. So the price per mile is greater under the tax. And note, this is the pump price that I'm referencing. Finally, is consumer surplus going to be greater under the new technology or the tax? It's pretty clear that this consumer surplus associated with the new technology is greater than the consumer surplus associated with the tax. And so, much greater consumer surplus under the energy efficiency policy. Finally, are there going to be more externalities associated with the new technology or the tax? Well, with driving externalities, it's usually a negative externality. Let's review externalities associated with driving. We have greenhouse gas emissions. We have reduced energy security. We have local air pollution. We have increased traffic, the more driving there is, and we have increased risk of accidents. If we were to rank those from the worst externalities to the smallest externalities in terms of a dollar value, turns out that traffic congestion and traffic accidents are going to be at the top. Then it's going to be air pollution, energy security, and probably the smallest one is the greenhouse gas emissions. Well, guess what? Under the energy efficiency policy, that is the performance standard, we're actually going to have more driving. There are going to be more cars on the road. That's just going to lead to even greater traffic congestion and greater probability of having an accident and potential death. So I would argue that the externalities are going up and are greater under the new technology than the gas tax. That's my video on performance standards and the rebound effect. Hope you enjoyed it.